To another video from the series. Today I decided to solve a Taiwan TST problem. It is number 1 from quiz 1 from round 1. So it should be relatively easy. And for this problem, I just tried it on my own first and I found a new solution. So I don't think that the solution that I'm giving you right now is uploaded in any other places. So I'm pretty sure this is original. And I was like so happy when I first solved it, but I realized that it's number 1 from quiz 1 from round 1, so it should be quite easy. Yeah. So first, what I did is I wanted to make something like so what if we have a plus b plus c here greater than or equal to 8 bc, something like here, and then we have something, and then we can write this so that later we can combine them. That was my idea. That way, if we add them and if we magically have equals 3, then we will prove our statement. I mean the inequality. So the first thing, this one is quite straightforward, and the reason is because we know that by AMGM inequality, this is greater than or equal to cube roots of a, B, C, and therefore this thing, is greater than or equal to 8 cube roots of A, B, C. Now I was trying to do the second one, but second one was quite difficult, and the reason is because, so in order to fulfill this one, we have to know that this one is true. So we know that this one is true. We checked it. So we know that we should know that this thing is greater than or equal to 1 over 3 times a plus b plus c. So if we prove this one, then we can add them and then thus prove our inequality. So let's write our lemma here. Our lemma is that a plus b plus c all over 3 is greater than or equal to a cubed plus b cubed plus c cubed. And the proof that I had was I wanted to use reverse mathematics, so we somehow prove it backwards. So because we know that a, b, c are positive real numbers, let's cube on both sides. So we know that a plus b plus c cubed is greater than or equal to 3 a cubed plus b cubed plus c cubed. Now let's expand this on this side. 3 times ab squared, no, a squared b plus bc squared plus c squared a plus ab squared plus a and bc squared plus ca squared plus 6abc is greater than or equal to 9 times a cubed plus b cubed plus c cubed. 9b cubed plus 9c cubed. Now rearranging our terms, we have 8a cubed plus 8b cubed plus 8c cubed minus 3 times 3 times I will just expand them. I don't know, like my solution is in my head right now. I couldn't really write them anywhere, so I might forget my solution in the middle, so I'm quite scared. But I remember factoring out a, because that way we can make like completing square, and that seemed really good to me. Minus 3c squared, so we use this one, and then I want to do 2bc, and the reason why I did them is because we can divide 6 by 3, and also I thought we can factorize this thing somehow. So we have b and then ab squared minus 3c squared minus 3a squared minus 2ca plus c times 8c squared minus the 3a squared minus 3b squared minus 2ab is less than or equal to 0. And we use all the terms, I think, because the reason why I didn't really have to think was because you know that this thing is cyclic. I mean, yeah, it is cyclic. And now here, because this thing is cyclic without loss of generality, let's say that this is true. Now here one thing that I did here is that, okay, why don't we find the maximum value of our left hand side? That way, if our maximum value is less than or equal to 0, then our lemma is true, thus we prove our inequality. And when is our left hand side maximum? Our left hand side is maximum. Wait, oh no, wait. I think my solution is wrong. When is our left hand side maximum? Our left hand side is, I thought our left hand side is maximum when a equals b equals c, but then I just realized that that's not the case actually. Yes, that's not the case. What should we do? So we know that our maximum for this thing will be resulted when a is greater than or equal to b and this is equal to c. That will result in the maximum value for this expression right here. But then we have to know that that will not be the maximum for the second one. Yeah. So it doesn't work. Wait, I think I need to think more about it. But wait, let's try it together. What can we do? So let's change our this thing as 2b squared to c squared b plus c squared. I think we can do that times a. Let me just use c because it's cyclic. A squared minus c plus a squared c squared minus 2a squared 2b squared minus a plus b squared is less than or equal to 0. So we need to prove if this thing is true or not. Now what then? When I think about it again, I think the maximum value will be resulted when all of them are equal to each other, right? And the reason why that should be the maximum is because when a equals b equals c, it implies that it is the maximum for this one. Also, when a equals b equals c, it just evens out everything. But I know that my explanation right now is not that rigorous. So I need to somehow find a way to make our proof rigorous. Now that I realize that I made a huge mistake. No. We need to prove Should we write our sub lemma? So our maximum value of our left hand side will be resulted when a equals b equals c. That is what I want to say. Yeah, I'm not sure if this is legal or not, but if we say that a equals b equals c, if we say that, this means that we are getting the maximum for this one, right? Just by looking at this one, we are getting the maximum for this, because without loss of generality, we said a is greater than or equal to b, which is greater than or equal to c. And in this case, we can think of it as wait. Now let's examine this case more carefully. What should we do? Actually, yeah, I just need to prove that the maximum value will be resulted when all of them are equal to each other. Now the maximum value for this is when a increases, b decreases, and c decreases, because a, b, and c are all greater than or equal to 0. Wait. No, positive, so it's just greater than 0. Greater than 0. Now let's think about the second case. For the second case, b should be the greatest, a and c should go down, and the last case, a should go down, b should go down, and c should go up. So when all of these make sense, yeah. So when all of these make sense, when all of these are true, then our maximum value for the left hand side will be resulted. And notice that the case when a equals b equals c evens out all these possibilities, right? Because if you only consider the first case and say that like a is an arbitrarily big number, b is like 0.0001, c equals like 1, something like that. But then our second and third case will not satisfy that, and thus will not result in the greatest. Now to even out everything, the only case is when a equals b equals c. So this case when a equals b equals c, it somewhat cancels out all the fluctuations, I will say, and provide the most decent and also the greatest value. Yeah, I think when a equals b equals c, the greatest value will be resulted, because think of AMGM inequality. For AMGM inequality, the more the difference, stabilizing our variables might be needed. Yeah. Yes. So think of AMGM inequality. When a equals b, that might not be like the absolute minimum, but it provides the absolute minimum when at least one of them are like defined, right? Now then, for the sake of clarity, let's just assume that without loss of generality, let's assume that only a is variable and b and c are constant. Oh yes, so this logic works. So when a equals b equals c, it will reach the maximum value, because when you think of AMGM inequality, when only one is the variable, and the other ones are constant, then the minimum value will be resulted when the variable is equal to the constant. So we can do the same thing here, and we can let A to become a variable and B and C to be a constant, because this whole thing is cyclic. So we have no problem here, like absolutely no problem here. We just consider B and C as constants, and we know that these constants can always change, so we are actually counting every single cases. So that's why the maximum value will be resulted when A equals B equals C. So when A equals B equals C, we get 0, 0, 0. Thus 0 is greater or less than or equal to 0. Thus we prove our lemma, and our whole thing is proven. Okay, so oh wow, this thing, yes. I'm not sure about how other people solved it, but I'm pretty sure they used other inequalities. The last part was quite confusing. I actually realized that I made a mistake while trying to explain my previous proof. So, good thing that I found it and actually correctly proved it. So I think our first kick is noticing this one, and the second kick is writing our lemma, and third one is using our logic here. This AMGM logic was quite difficult, I think. I mean, yeah. If you think the solution is not perfect, and if you think you have better solutions or any comments based on this solution, please feel free to leave them in the comment box below. I'll try to be sure to answer them. And thank you, and see you tomorrow with another fun problem. Thank you and bye.